This is Gallus Domesticus. I'm Art Turlip, and we're going to do some electrical engineering. I don't know why I have a chicken. I really don't. Let's get started for today. Before we launch in, I wanted to note for those of you that are watching these on time that the first real quiz is going to be on Friday, June 19th at 2:30 p.m. We've talked about this at length through email communication. If this confuses you for some reason and you haven't been paying attention, what we're doing is a 30-minute quiz. You have 15 minutes to download it or you can view it on your computer, that's fine. And 30 minutes to, 15 more minutes at the end to upload the document. So you have plenty of time, even with limited internet access. I'm out here in the middle of nowhere, and I have managed to be able to do that just fine off of a cell phone hotspot with limited connectivity. So if I can do it, you can do it. The rules for this quiz are as follows. Okay, you may not discuss this with peers during the exam until during the quiz until 5 p.m. Saturday, June 20th. And if you break the rules, okay, I'm going to be very angry. Yeah, that's me, angry face. It's not good. You don't want to see that. I turned into a cartoon, apparently. Okay, so please don't discuss it with other people. Please don't use the internet for your quiz. These kind of problems are so specific, I doubt that it would do you much good. Most of the cheating that's occurred so far has been, and the one I have the problem with the most, honestly, is not presenting your own work, okay? That is a huge, huge breach of academic honesty, and at the end of the day, you're only going to be shooting yourself in the foot because you're going to have to know it when you do a job interview or something. Okay, it'll cover chapters 1 through 4 of the book and all the associated homeworks, so all the homeworks that are tied to chapters 1 to 4. I'm doing a little bit of moving furniture for those chapters right now, so hopefully everything will be squared away by the time we get to this point about a month from now. And it'll cover the lectures 1 through 4 as well. You should take no longer than a half an hour, okay? You're on your honor for this one. I know some of you need extra time, and that's and you've talked to me about that. You have university approval for that. No worries there. Some of you are in different time zones. You're going to be timed on your requested time slot. And again, I emphasize, please don't discuss the little quiz with anybody until June 20th. All right. Enough of that. Oh, what we're talking about today is current sources and MOSFET non-ideality. All right, so I had to do a little bit of fellow kids memeing here, I guess. So there you go. There's your Spider-Man meme. We're gonna look at the general applications of MOSFETs. In particular, you've seen current sources in the past, and we're going to show you how to generate a current source using what's called a current mirror. And as you might guess, this involves two identical MOSFETs. So you have an IREF, the reference current, which is running down through a resistor, and that resistor may be variable or fixed, but doesn't really matter. The M1 and M2 have identical parameters. So each of these MOSFETs are from the same batch. And what ends up happening in this configuration is that the current that we have for IREF is going to be the same as the current that we have for IOUT. And so in this way, technically this isn't a source, this is a sink. And we're going to talk about how to make a true source later, which actually is just switching these NMOSs to PMOSs. But that's pretty much it. This is a really cool thing. So a couple of things to point out. I think I do it, right here. So how does this even work? Well, we have M1 is tied to the gate. Its own drain is tied to its gate. So remember that for MOSFETs we have drain, source is where the arrow is, and then G is our gate. So we actually have this linkage between our drain and our gate. And that's only on the reference MOSFET. Now, what does this do for us? Well, we're going to have to look at the equations to see why this has any, or what this is really doing. So let's take a look at IREF. IREF is defined, IREF is defined as ID1 sat. That makes sense. We did this last time. And because we're in saturation mode, okay, we know that we can use this equation. Nothing new there. However, since the gates and sources are tied together, we have to have this be true. So our gates here and here are tied together, and our sources here and here are tied together. So this condition is true. All right. Since they're from identical batches, we know that Kn1 is equal to Kn2 because they're the same MOSFET, effectively. And the threshold voltage, which is also a function of the device, or it's rather a given with the device, has to be the same between the two as well. So when we rewrite this equation for I out, the current flowing through the second MOSFET, it's equal to 1/2 Kn2 VGS2 VTH2, but we've shown and we know that all of those 2's can actually go to 1's, and what do you know, that's the same as IREF. So the way in which we've constructed this circuit makes those things true, which changes our equation, our saturation equation, over to make this current mirror what we put in as a reference. So now I know for the summer session there's sort of this difficulty because you can't take the labs concurrently with this course. So you've either taken the labs already and you understand most of the stuff, or you haven't seen the labs yet. So let me make a note. When you do the lab component for this course, you're going to combine multiple MOSFETs to make maintaining the bias of M2 much, much easier. So in theory, what you normally have here, there's some kind of circuit out here. Okay? And that's what you're going to be pulling or pushing the current through using this current mirror. So it's a very important tool to have in your toolbox. It's a way to use a MOSFET that's very effective. All right, so let's expand just a little bit further. If we don't have identical MOSFETs, let's say we change I out by adjusting the MOSFET parameters. Let's say we don't have two Spider-Mans. Maybe we have Spider-Man and Venom. Okay, they're kind of similar, but they're a little different. Well, then what happens? Well, let's say that M2 has twice the channel width. Then we know that Kn, which, recall, is determined by the length, the width, and that oxidizing capacitance, and also another coefficient, the mu. But in any case, if it's 2 times the channel width, we're going to have twice the Kn. So if we do that and we plug that into the equation, you can see that it's going to change how that current is affected as well. So you can actually control, you can actually set a different I out based on changing the relationship between the two MOSFETs. That's the best way to say that. All right, So let's focus on the fact that VGS is actually equal to VDS. Recall, as we just mentioned, that VGS has to be the same as VDS. Why? Well, because our drain and our gate are tied together. So G and D, for all intents and purposes on our first MOSFET, are interchangeable in a way. I mean, they are because they're tied together. So IREF we can rewrite in terms of not VGS, but instead VDS. Well, we have a way to write VDS in terms of IREF, right? If we look at the current that's flowing through VDS, we know that it's just that our voltage source minus IREF times RF, which is that voltage drop that we have across this resistor. So we have VDS occurring now in our big equation. I say big, but it's the important equation. It's our ID or our IREF equation. And we also have VDS right here. So what we can do is actually substitute this in, and we're going to get a new expression that makes life really easy. So when we plug this guy in to here, we end up with the following. IREF, over here, IREF is equal to 1/2 KN1 times all this stuff. V plus minus IREF, RREF minus VTH1, quantity squared. So the takeaway is that we have a relationship between IREF and RREF. Okay, sync to source. I promised we'd chat about this for a moment, so let's do that. As previously noted, our NMOS is a current sink. To make it a current source, no surprise, we just have to switch our design to be a PMOS. And what it looks like is this guy here. So we have our output. Again, current's flowing down our MOSFET. We like to try to show this in this orientation whenever we can, where the current is flowing down. Sometimes it's not possible, obviously. But for this example, it is, and it works nicely. So there's really no difference here between these two diagrams. It's just upside down and replace NMOS with PMOS. And you'll notice here that the gate and drain are still tied together. And the only thing that's really changed is our orientation. So there you go. That's how you create a current source for MOSFETs. All right, switching gears. So this is going to happen a lot where, I'm sorry, but I lied. All right, this is going to be kind of a running theme for the course. What we're going to see is that ideal behaviors don't actually exist in reality. And one of the things that we can do is exploit some of the non-idealities for certain kinds of analysis. So soon, and in fact I believe it's next chapter, we're going to talk about AC analysis of MOSFETs. And one of the non-ideal behaviors is the fact that output current that we talked about, ID sat, is actually not quite constant. Recall that we had VDS, ID down here. After we hit a certain point, we get the knee of the curve, and it plateaus. Remember we said, oh, it doesn't go any higher than that. It's stuck there. Well, that was a lie. I'm sorry, but it was. What actually happens is you can have this behavior. And this is a good approximation for the capping is a good approximation. But what happens is the increased DS potential produces an inversion layer at the GD interface, which allows for another means of current to the drain. So effectively, that pretty diagram we had in chapter 13 of your EE1 textbook, and you've kind of seen this before, is, you know, it's ideal. But you effectively end up with an extra bit of current that's going up linearly with respect to VDS. So you do get a little bit of push through, a little bit of bang for your buck. And this is a not quite to scale, but you can see our VDS sat here for all of our different VGSs. So recall that as VGS, at least for the NMOS case, as VGS is increasing, we get these steeper and steeper curves going up. And the knee of those curves right here is VDS sat, where it becomes saturated and plateaus, or in a more particular way, it follows a less steep linear behavior, which is determined by the device. So in practice, in order to find this, linear parameter, you can extrapolate backwards from the behavior of a device to find this VA point, which is just the 1 over lambda, which is just the parameter that we use to kind of classify. It is referred to as the channel length modulation parameter. So that's important to know. You may see that on some sheets. So it's a good thing to have in your back pocket. Okay, we adjust our ID equation as follows. So before, we had this guy, right? So now let's take a look over here. This is our new version. And you can write it either way here, but there you have it. So what does this actually mean? Well, if we look at the new version, which I'm just transferring down here, then we have what effectively acts like a constant. Remember, the ID sat was just a plateau or just a constant function, right? ID sat, you couldn't go above it before. Now, that constant is going to act like a slope and part of an intercept parameter for us. Or it will be the intercept parameter and part of the slope. So let's take a look. If we multiply this guy through, then what we end up with... Sorry, let me get rid of some of this chicken scratch over here. What we end up with is I'm all over the place. It's a constant times our variable, which, as a matter of fact, what color do I have for this? There we go. Which is, in fact, our x-axis here, right? This is our x-axis. Plus some constant. So you can think about this as being that, being the intercept, really. And you could, for linear equations, you can kind of move around and do the, do some funny business to make it either an x-intercept or y-intercept. So you can think about it as being on here, or more importantly, back here. And that's pretty much it. So we can use the fact that this increases linearly next time. And right now I'm going to launch into some additional examples from the homework to kind of clear up some concepts before we move into the small signal models and active loads. Let's start with all the problems in homework 3. We're actually going to work through all the ones I currently have. I hope to add a current mirror in here at some point, but we'll see how that works out. Okay, so let's get started with this problem. We're given a couple things for this circuit. We know that VTH is equal to 1 volt, and we're asked to determine Kn for V out equal 1 volt when V in is equal to 5 volts. Okay, let's draw out our circuit real quick. We have a 5 volts up top, a resistor of 10 kiloohms, V out. We have our MOSFET. Goes to ground. And then over here we have our V in. All right. And we're going to call this guy M1. Okay, so let's make a few observations right off the bat here. We know that VTH is equal to 1. If we were given that this was the absolute value, of course, this would have to be positive because we're dealing with a NMOS here in enhancement mode. So you should be able to recognize that. For V out equal to 1 volt, we have, I don't know what's going on with that. All right. We have a 4 volt drop over our resistor. And we can see that pretty easily here. So we have 5 volts up here. If V out is equal to 1 volt, then the drop across this resistor has to just be equal to 4 volts. So we do a little bit of Ohm's law. And we end up with ID equal to 0.4 milliamps. Remember that this is that current that's going to go into our drain. So recall this G and D S. So whatever current we have here is going to be flowing in to our device. Okay, so we've solved for ID. Now let's look at VDS and VGS. So first, VDS. Okay, let me go ahead and color code this a little bit. So let's do just a little squiggle here. All right, and let's do some green for VDS. So for VDS, it's the potential between here and here. So it's equal to V out, right? Because here's our V out. And we're looking at the potential between that and the ground. So it's V out, technically minus 0. But it's just equal to whatever V out is equal to. And we're given that V out is equal to 1 volt. So VDS must be equal to 1 volt. Splendid. Now if we look at VGS, Gulf Sierra, we have the potential between these two. Well, that's just VN to ground. So you should be able to recognize that pretty easily. VGS is equal to VN. Again, kind of this hidden minus 0 because we're going to the ground, which is just equal to 5 volts. Now, in our equation, if we're writing this out, we know that for, we should note one other thing. What mode are we in? Right? What region are we operating in? Not what mode. We know the mode is enhancement mode, right? The region that we're operating in, is it saturation or is it triode linear? Have we met the threshold voltage? Well, here's our VGS. So VGS is greater than VTH. This is equal to 5. This is equal to 1. So not cut off, i.e. we're on. Ding, ding. Okay, so now we need to figure out if we're linear triode or if we're saturated. So how do we figure out if we're saturated? Well, we need VDS sat. So VDS sat is equal to VGS minus VTH. Well, fortunately for us, VGS is a fixed quantity here, and VTH is also a fixed quantity, right? We had it up here. So this is going to be fixed for us already, just because VGS is already determined by our givens. More particularly that one. Okay, so we go ahead and plug these values in. We have 5 volts minus 1 volt. That equals 4 volts. So is VDS greater than VD sat? VDS sat? No, it's not. Nope. So we are in triode linear region. And for that, we use our handy dandy equation. We have, I'm going to color code this for you with our handy dandy equation. Kn, oops, we got to write our ID here. Let's do that in purple. So ID is equal to Kn times VGS minus VTH times VDS, and then we're going to subtract off 1/2 VDS squared. Okay, that's our triode linear equation. Now we have all the pieces that we need here. We have ID, we have VGS, we have DS, we have DS, we have VTH. The only thing we're missing is the thing that we're looking for, Kn. So the easiest way to do this, instead of rearranging all of our algebra here, is just plug it in, simplify, and then do the algebra. So we have 0.4 milliamps is equal to Kn. VGS is 5 minus VTH is 1 times VDS, which is 1, minus 1/2 times VDS squared, which is also 1. So this is going to cancel out nicely here. We have Kn is equal to 4 times 1 minus 1/2. So should be 3.5 over on the right hand side. 3.5 Kn. We'll put a 0 in front because we're good engineers. We're going to always include that 0. And then from here we can solve directly for Kn. Kn is equal to 0.4 over 3.5, which you can reduce if you want to. But that's it. And remember, our units on this are going to be milliamps over volts squared. Okay? And you could have seen that here too. This unit here was trailing along volts the whole way through. Or excuse me, volts squared after you multiply the two together. And then we had milliamps over here. So the units are correct for what they should be. Note that you may encounter a problem on an exam or something like that where this is not necessarily true. I encourage you to make sure that it is in the correct format so you don't get confused later on. So, but by and large, I'm not going to try to throw too many curveballs at you guys just to trip you up. I don't play that way. Okay, so that's our solution for that. Not too bad. The biggest thing here was just kind of the setup. I hope the colors kind of helped you follow along a little bit here. That's it. Let's go to the next problem. Let's take a look at homework 3 again. And we're going to look at problem 1B. And I'm going to update this. So If it's not reflected in there, it should be. But I'm going to let Kn equal 1 milliamp per volt squared in this problem. And we're also given the fact that VTH for this problem, absolute value, is equal to 2 volts. And we're told that this is a depletion mode MOSFET in the depletion load configuration. I out over here. Getting a little messy over here. There we go. Okay. Zip. We're going to label this M2. And what we're asked to find is plot ID as a function of, or with respect to, that's what WRT means, V plus over the range 0 to 10 volts. Now, at first, this problem may seem a little intimidating because, you know, to plot anything, you got to pick a bunch of little points along the way and figure out, okay, where does everything go? I probably at least need, like, 10 points here or something like that to plot, or maybe 5. It's not actually that complicated, and when you break this circuit down, some things become apparent very quickly that make this a very, very easy problem to approach. So let's take a survey of everything that we have going on. I always like to label these. So we have, this is an NMOS in D mode. So recall that in depletion mode that we're dealing with, if you look at a number line here, there's 0. Our VTH is going to be down here. Hello, negative something. All right. And we just have to be above that value for our VGS to be on. Okay, so it's really not too much of a difficult requirement. Recall that with D mode MOSFETs, depletion mode MOSFETs, they're pretty much always on unless you do something to turn them off. And that's the kind of situation that we actually have here. So notice that our gate and source are tied together, which means that VGS is shorted out, so this is always 0. We have no potential between those two because they're wired together. That being the case, we know VTH is negative because it's NMOS D mode, and therefore VTH is equal to minus 2 volts, which we're getting right from up here. That's a given. So we meet the requirement to be out of cutoff. Oops. i.e., we're always on. And that's a really important feature of this particular problem. As soon as you recognize that, this problem becomes very easy. Because if it's always on, then we're always going to allow current to flow if there's a presence of VDS. So now all we really need to figure out is the difference between when saturation occurs and when we're in the linear triode region, because we're never actually in the cutoff region. So here we are. There's one other important note, and that is V plus is coming down here. And let's calculate some voltages real quick, or think about what VDS actually is. So VDS is in fact equal to, V plus, which is also equal to V out. Why is that? Well, these two guys are tied together. Oops, let me do a different color. It's too pink. These two guys, glitching. These two guys are tied together, so their voltage has to be the same. D to S just goes to ground from here to here, or if you're comparing here to here, we're just going to ground. So our potential across DS, you can kind of imagine this node here collapsing down to our point at D, and this guy here collapses down to our point at S. And so VDS, that potential between D and S, must equal the potential between V plus and the ground, or I out in the ground. They're the same thing. So it's just a matter of collapsing that circuit down to something that makes sense to see that's true. Okay. Enough pink scribbles everywhere. With that piece of information in mind, this is just a typical plot that we have for VDS, i.e. V plus, versus ID. And our key point here is going to be VDS sat, right? Our saturation point. Our saturation point, we should well know, VDS sat is equal to whatever VGS is minus the threshold voltage. Well, this guy is fixed, and this guy is fixed. As a matter of fact, this is fixed at 0, and this is fixed at -2, so this is equal to 2 volts. So we know that this is right at 2 volts. We know that this region is the saturation region, because as we increase VDS beyond the saturation point, we're in the saturation region. And before that, all the way back to 0, we're in the linear or triode region. So now we're getting somewhere. Furthermore, I know that for our DC model purposes, that when I'm in the saturation region, this is just a horizontal line. And actually, I'm going to draw this a little bit thicker in a different color so that it shows up better for this. So here's my graph. So this is fixed at ID sat. Okay, whatever that may be. Now for this problem, as it turns out, ID sat is going to be equal to what? Well, we know that ID for the saturation region is equal to 1/2 Kn VDS sat squared. This is 1. Actually, let me write it this way. I like to do this sometimes. You know, you can cross that out, go to 0, or cross that out, go to 1 when you're just multiplying through. Makes it easy. VDS, this is going to go to 2 squared, so that's 4. So this is just equal to 2 milliamps. And then for the other points, so now we've got already all the way from 2 to, let's call this 10 volts. Wow, we are 4/5 of the way done with our problem. This is fantastic. Now all we have to do is grab a couple points in here to figure out what this curve looks like. I'd say you grab this guy, we already know what that is. So at 0, we know that it's got to be equal to 0. So we're done with that. Let's say if you grab 1 or 2 more points in here, you're done. All right, so we actually didn't have to do hardly anything for this problem. So let's pick 1 volt. And we know that we're in the linear triode region. But let's let VDS equal 1. So we have ID is equal to, and I'm just copying, I'm going to write the equation out first. VGS minus VTH, VDS minus 1/2 VDS squared. This guy goes to 1. This guy we know goes to 2. And this guy is equal to 1 milliamp. So we're left with ID is equal to 2 minus 1/2 times, this is VDS squared, which is 1. So this is equal to 2 minus 1/2. It's equal to 1.5 milliamps for VDS equal 1. So right here in the middle, we're going to have this be 1.5 milliamps. Frankly, I think that's sufficient because this is a nice smooth curve. So if you did that, I'd be very happy. I will probably be more specific about how many points I need appropriated here, because being from a math background, I like to be very specific about what I'm asking you. So this floats the boat for me. This works. We're done. This is the whole problem. We spent more time chattering about the things that we know already and probably knew off the cuff than we did actually solving the problem. So it's all about setup, and it's all about just surveying what you're looking at first, writing down all the information that you have, and then pushing through the problem. That's really the key to being successful at this. Additionally, a couple notes about the homework. Not perfect, and I helped write some of these. I helped latex some of them. Others I haven't honestly even looked at too much. So if you see any kind of issue with any of the homework solutions or problems, please let me know right away so we can share that among all the other students. And, you know, if you're confused, someone else probably is too, because there's 90 of us in this class, okay? So keep that in mind as we move forward. And let's begin on this problem. Okay, so for this one, we have Vn on the left-hand side, and it's going to feed into our two gates. And let's draw these MOSFETs here. M2 here. And we're supplying it with 5 volts. And this guy here is just going to ground. And we'll call this one M2. And then we have V out off to the right-hand side. Okay, we are given the following. VTH is equal to 1. K is equal to 2 milliamps per volt squared. And in big red letters, because I don't know about you, but whenever I have a test or something, I always like totally space out on what I was even solving for. So I tend to underline those things or spell them out really explicitly so that I don't forget when I come back to it and check my work or do something. V out is what we're looking for. So we want V out for Vn equal to 0 or 5 volts. Quick side note. Oops, let me do this in a different color. Let's do green, a little light green. So side note, the mathematician in me can't resist. We have a couple different things that you should be aware of by now, I hope. So this guy is, if you're looking at a number line, is all the points between 0 and 5, including 0 and 5. This guy is all the points in between 0 and 5, not including 0 and 5. And this is just equal to 0 and or 5. All right, it's the set of those two elements. So it's important to know the difference because it's going to keep coming up if you don't. So anyway, good review. All right, moving on. What do we know? Okay. First thing that jumps out at me is, this looks like a current mirror. No, it's totally not a current mirror. Just, it's not even close. But it is something really cool. It looks like it from the side if you tilt the screen, and even then it's not. But it is cool. All right, so we know it's not a current mirror. What the heck is this thing? Let's find out. We have our gates are tied together. We have that our drains are tied together. We know that, just from looking at it, M2 is a PMOS, and M1 is an NMOS. Aha. So that's going to be important when we start to consider our VTH, right? Remember that the rules for VTH on PMOSs and NMOSs are different. So if you haven't started doing the homework on number 1 and homework number 1 and 2, you might want to go practice that if this is not familiar. All right. We also know, if we start thinking about VN and everything else, actually, let's go ahead and do the VTH thing first. So VTH, since we're on the topic, VTH1 must be equal to 1 volt, positive 1 volt. I'll write a little positive here just to emphasize. And VTH2 must be equal to minus 1 volt. All right, last thing before we launch in, VGS1. So we're looking at the potential. Let's do this in purple. Purple for potential. Between here and here and here and here. So we're looking at those S's. VGS. Remember, I'm just going to label it real quick. G, S, D, G, D, S. All right. VGS1. Oops. I know some of you were screaming for a while. Okay, it's there. It's 1. Don't freak out. Don't panic. I fixed it. All right. VGS1 must be equal to just VN. It's really straightforward. Because we have VN, we have ground. The difference between those two is just VN. All right, so VN minus 0. For VGS2, we have VN minus that positive 5 volts. So it's VN minus 5. Okay, the first condition we want to solve for is when VN is equal to 0. Now, if VN is equal to 0, we can use our handy-dandy rules that we came up with right here, our setup, in order to solve for our V out, or at least logic our way through it. So we know that if this is true, then VGS1 is equal to 0. Well, that's not going to make our meet our threshold requirement, right? So M1 is OFF. It's in cutoff mode, or cutoff region entirely. So if M1 is completely off, then there can't be any current going through here. And if there's no current going through here, then there can't be any current going through any of it, right? Because if there was current going through it, then it has to go somewhere. So we have a little bit of a dilemma. So what happens at our other MOSFET? Well, at M2, oh, it's most definitely on, right? So, because VGS2 is equal to minus 5. And remember, this is a PMOS, so it just has to be more negative than the threshold. So we know that over here we noted, okay, that VTH2 was equal to minus 1 volt, And I like to think about PMOSs, or in this situation, as not, figuring out the direction on the Pac-Man signs, the greater than, less than, but just think about it in terms of absolute values. So is the magnitude of voltage, the absolute magnitude of voltage, greater? And in this case it is. So this is greater than minus 1 volt, equal to VTH. Okay. So if it's on, but there's no current, oops. The only way we can have that is if we have VDS2 equal to 0. Again, because we have no current. We can't have VDS2 greater than 0, because otherwise that would contradict the fact that we have no current. We know we have no current. So if VDS2 is equal to 0, then it follows that Vout is equal to, there's no voltage drop here, right? That voltage differential is 0. So we're just looking at the differential between these two, which is just 5. So it's 5 volts. So for this input, we get this output. What about for Vn equal to 5 volts? Well, then similarly, VGS2 must be equal to 0, right? Because of what we said right here. So if VGS2 is equal to 0, M2 is off. Again, it's the cutoff region. And once again, we see that conversely, M1 is on this time, because VGS1 is equal to Vn. Well, that's just 5, which is greater than 1, which is our threshold. So it's on. It's allowing current to flow if any VDS is applied. So, again, we use this assumption, there's no current. Oh no. So that means that VDS1 must be equal to 0, because we know that it's open if it was letting current flow through. If it's not letting current flow through, then this has to be equal to 0. Otherwise, it would let it through. Okay. With that in mind, we know that Vout, looking at the potential here, we have just the difference between the ground and Vout, because the potential difference here is 0. VDS1 is 0, right? And therefore, Vout must be equal to 0 volts. We'll do this in, I don't know. How about a happy pink color? Ah, very interesting. So we have an inversion happening between 5 and 0. Basically, it's turning an input of 0 into an output of 5, and an input of 5 into an output of 0. That's a pretty cool device. All right.